All right, so we'll start our discussion of mixture thermodynamics with physical observation that sometimes volume additivity does not apply to mixtures. And so the example here is that if we mix 50 milliliters of ethanol with 20 milliliters of water, we get a total solution volume of 67 milliliters, not 70 milliliters as volume additivity would suggest. And so the simplest case scenario that we could think about for analyzing the molar volumes of mixtures would be to say that the molar volume of a mixture is just the mole fraction weighted sum of the pure component molar volumes. So graphically, this looks like a linear relationship connecting the molar volumes of the pure components on a molar volume versus mole fraction plot. Such as the one that we have shown here. And we've got potentially two examples here, two different sets of pure component molar volumes connected by these lines. And so that mole fraction weighted sum of those terms is shown here now on the screen. And so in reality, the simplest case is not always observed. And so, for example, with carbon tetrachloride and benzene, those solutions have volumes that exceed the simplest case, and ethanol and water solutions have volumes that are smaller than this simplest case. And these changes in volume upon mixing result from interactions between the molecules in the mixture. And as chemical engineers, we really need to be able to describe this phenomena from a thermodynamic perspective, because you would certainly want to know if mixing two streams in a chemical plant or in the laboratory was going to result in a substantial change in volume upon mixing, as this could end up affecting design criteria. And as we'll see, we can also apply these same ideas to things like enthalpy, which could be very important in terms of managing heat in a reactor or in different parts of a chemical plant or an experiment. So a common theme in mixture thermodynamics is that we often seek to connect the properties of the mixtures to the properties of the pure components that make up the mixture. So we'll consider a process where we seek to make 1 mole of a solution from components 1 and 2. And so components 1 and 2 each have a volume and an enthalpy associated with them, and the final mixture has some volume and enthalpy associated with it. If we want to do the mixing process at constant temperature and pressure, we may need to either add or remove heat from the system due to the enthalpy change upon mixing, and this is listed here as a delta H mix term. The change of a property upon mixing, delta V or delta H mixing, here we're showing delta V mix, tells us about the difference between the property, V or H, here in this case we're looking at V, of the real mixture and the mole fraction weighted sum of the pure component properties. This delta V of mixing can be determined if we know the pure component properties and the property of the real mixture. In other words, we go in the lab and we actually mix the solution up, measure the volume, and compare that to what we'd get if we evaluated the sum on the right-hand side of the equation. But additional information is ultimately needed if we want to do predictive calculations of the real mixture property. And frankly, from a practical perspective, that's often the situation that we're in. We want to calculate delta V of mixing so that we can ultimately figure out what the volume of the mixture is going to be. It's also worth pointing out that we can correspondingly write out changes of property upon mixing expressions for many of the usual thermodynamic properties. So we see things here like enthalpy, internal energy, entropy, and Gibbs free energy. And so we can write the corresponding relationships very much in the same way. And a lot of the analysis that we're doing here can be applied to these different processes. Turns out in many cases that volume and enthalpy are a little bit easier to conceptualize, but they can be applied to many of these other properties as well. All right, so graphically, delta V mix is the difference between the real solution molar volume and the mole fraction weighted sum of the pure component molar volumes. And so we see that illustrated here on the graph that we were just looking at. For carbon tetrachloride and benzene, it's a positive value. For ethanol and water, it's a negative value. And so, because this change in a property upon mixing is telling us about the difference between the real mixture property and this simplest case mole fraction weighted sum, the sign, whether the delta V or H of mixing is positive or negative tells us about what is going to happen upon mixing. So if we think about both enthalpy and volume, we see that if delta H mix is negative, for example, the mixing process will be exothermic. And if delta V mix is negative, then the mixture will contract relative to the volumes of the pure components. And of course, the opposite will happen when the change upon mixing terms are positive. We'll have endothermic mixing, and we'll have expansion upon mixing of the mixture. And in special cases, including ideal mixtures, the change of properties upon mixing are going to be equal to 0. And so ultimately, we want to calculate delta V mix, for example, without knowing the real mixture molar volume ahead of time. And so in order to do this, it's useful to start by writing a total differential for the total volume of the system in terms of temperature, pressure, and moles. And so we can write that out as shown here. And so total differentials in general allow us to see how a particular property, in this case total volume, depends on other properties, here temperature, pressure, and number of moles. And the derivatives that we get in this total differential give us this information. And so you should be familiar with this approach from your prior thermodynamics training. Here for today, we'll focus on the last term in our total differential, as we're interested in understanding how mixture volume changes in response to changes in composition. And so the derivative in this term that we've highlighted here is defined as a partial molar property. In this case, this is the partial molar volume. And so this term is telling us about the differential change in the total volume of the system upon addition of a differential amount of one of the components. It can be dependent on composition, in other words, adding a little bit of component A to a lot of component B can be different from adding a little bit of component B to a lot of component A. And so the order of mixing, or where we are on the compositional scale, can really matter here. It's also important to have a conceptual understanding of what partial molar properties actually mean. The partial molar volume is perhaps the most intuitive, since it is somewhat easier to think about differential changes in volume upon addition of some differential number of moles of a component. But as we'll see, other partial molar properties, such as partial molar enthalpy or partial molar Gibbs free energy, are also really important in terms of thermodynamics. And so the partial molar properties can be defined for a number of other variables as well, and so we'll see how we can replace V with H or G in particular, but we could do this for other properties as well. So let's consider a simple example, pouring coffee. So we will consider the enthalpy change upon moving the coffee from one state, perhaps in the French press, to another state in the cup. The partial molar enthalpy is defined using the total differential approach. We're using enthalpy this time instead of volume. And so we see here that at constant temperature and pressure, the total differential simplifies to the expression at the top right. And you should go back and make sure you're comfortable with using that total differential approach to get to this point. So this expression then can be integrated from one state to the other to determine the total enthalpy. And so since enthalpy is a state function, the path of this integration is arbitrary, so the result shown here applies for other state transitions as well. The key result is that the total enthalpy is expressed as the sum over all of the components in the system of the product of the number of moles and the partial molar enthalpy for each component of the mixture. So it's important to note the use of partial molar properties here being different from the use of pure component properties. And so it's really important to recognize the distinction that's being drawn here between the two expressions that we have in the middle of the slide. So we could normalize the total number of moles in the system to determine the molar enthalpy of the mixture from the total enthalpy as described here. And again, it's important to get comfortable with using contextual clues to identify the units of the variables in these expressions. As we see in the lower left, partial molar properties can also be used in the fundamental thermodynamic relationships that you've learned about in previous thermodynamic courses. For example, the fundamental relationship for partial molar enthalpy can be expressed in terms of the partial molar internal energy and the partial molar volume, as we've shown here. So the connection between the total property, either perhaps enthalpy or volume or others, can be used to help us determine the value of the change upon mixing term. Here we switch back to talking about volume, and we'll consider the volume change upon mixing term. This is the delta V mix definition that we've used earlier, and so we have that up here on the screen. In this situation, V is the total volume divided by the total number of moles in the system, and we can relate this V total to the partial molar volume as is shown on the screen. When we combine everything together, we see that we can calculate delta V mix with knowledge of the composition of the mixture we would like to make, the partial molar volumes of the components in the mixture, and the pure component molar volumes of the components in the mixture. And so this approach can readily be applied to enthalpy and other thermodynamic properties, but it's really important to see here how we've taken this partial molar volume and these pure component molar volumes, we match that up with the composition of the mixture we're looking to make, and that allows us to get an expression for the delta V of mixing, which we could then use to back calculate out the volume that we'd expect for our mixture based on the aspects of the mixture that we're proposing to make.